Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Yes, welcome to my talk. So this is conjoint work with Arjun Jain, who is a PhD student with me, Tobias Ritschel, and Hans-Peter Seidel. And the title is Exploring Shape Variations by 3D Model Decomposition and Part-Based Recombination. So I recently became interested in looking at 3D models, databases as they are available on the internet. So maybe many of you have heard about Google 3D Warehouse, there's TurboSquid, there's Dosh 3D and many others. And there we have these perfect 3D models modeled by designers who know how to do this. And the idea is now, can we harvest this information to provide new modeling tools, easier modeling tools that are maybe accessible also for novice users. And here you see a robot from this database, and it's composed out of many parts. And there are other robots in this database. And now the question that we pose is, can we generate a blended shape between these two robots? Or if we have even more robots, can we generate a blended shape between these three robots? And obviously we can. So this is here our system. And as you see, it has a very easy user interface. So there's a slider user interface. And when the user moves the slider, the system automatically interpolates between these shapes. So I have to say these shapes are not anyhow annotated or something. This is a fully automatic analysis, and this is the result that you can get out of this. So here we now combine a third robot into this. So here you see a system overview of this tool. So input to the tool is all the database models. Then we perform a shape analysis of all the models. This is in the offline phase. Then we store all the pre-computed data serialize it onto disk. And then we perform, on the online phase, we use this information to perform an interactive session where we do shape synthesis and generate new models. Okay, so I first want to talk about the shape analysis part of this pipeline. It has several steps. So first is segmentation, then there's contact analysis, symmetry detection, and hierarchy. And now here in this video, you kind of see a fast forward of these steps. So first we perform segmentation, then we perform PCA, we perform contact analysis, and we all do this in a hierarchy. So here you see different hierarchy levels for the segmentation, different hierarchy levels for the segmentation into PCA, and several hierarchy levels for the contact analysis. So I go now through all these steps in a bit more detail. So on the left you see the input model, and the first step is to segment this model into parts. And there we assume that the designer, while creating this model, has already created it from parts, but while storing it in the internet repository, maybe as an OBJ file or something, this information is usually lost. And so what we do is we look for connected mesh components, and this we can simply do by doing region growing on the connected components. And this gives us this part representation, and this is the finest representation that we can get for the parts. Then we sample the surfaces of the polygonal mesh to a point cloud, and on each point cloud of a part we perform a PCA, and this PCA gives us a local coordinate system for each part. You see here these boxes, these are the individual local coordinate systems for all these parts of the robot. So you see it's composed out of maybe 200 parts or more. Next, we perform a contact analysis. This gives us the structure of this object. So here you see the connections between parts that are almost touching each other. once we have that, we run a symmetry detection step. And in this step, we kind of random sample two similar parts. Maybe these are the 2 foots or something. The 2 foots define are 3D points in space, and so that they define a symmetry plane, and then we look how much the other part supports this maybe symmetry plane. And this gives us the dominant global symmetry transformation, which we call H. Now, with all this information, we build a shape hierarchy. So, and this goes from a coarse to fine level. So level 0, k equals 0, is the coarsest representation. There, all parts of the object are kind of glued together to one part. And then in each next level, we kind of split the object either into 2 objects or into 3 objects, dependent on the configuration. And during this splitting operation, the symmetry of the object is taken account, and we also enforce that parts are always connected. Okay, so we do these for all the shapes. We have all this information now in our database on disk. And now in the online mode, we do perform shape synthesis. And this consists of shape matching, shape interpolation, and a contact enforcement. So I start with shape matching. So one approach one could think now is that we have our hierarchy for the source shape, and we have our hierarchy for the target shape. And maybe one could look at a certain level, maybe k equals 2 and k equals 3, where both of them has approximately the similar number of parts. And now the task is, okay, which parts could match? And as we see, this is very difficult because maybe, this car has 1 tire, whereas the truck has 2 tires. Maybe one word about the visualization here. So the 2D polygons are the parts on the finest level, and the color coding is what is one part on this particular level. So what we tried first to match these things is we performed spectral graph matching. We have a graph because we have this contact analysis. So we said, well, maybe we could run spectral graph matching. But the best maybe assignment even one could do manually is maybe this one. And why is this not perfect? Because the segmentations of these both these objects are not the same. So we learned while doing it, maybe we need to update the segmentation while matching. And this was actually the key success to make our approach work. So what we do is we kind of first rebuild the hierarchy to have a similar segmentation as the source shape. Okay, here's the comparison. On the top you see our original approach, and down there you see like what would be the matching color-coded with our new approach. So okay, so now I go in a bit more detail. How does this shape matching work? It's very, very simple. So on level 0, as I said, all the parts belong to the object, so the object is assembled out of all the parts. Then on the next level, we split it into 3, so the main body of the car and 2 tires. And we also know now the center of the collection of the parts, and we know the center of both the tires. And what we do now, we just move these boxes over to the right and see now, which parts are closest to the centers. And for the upper part of the truck, these are assigned to the green ones, and the lower are assigned to the orange one, and the purple one is assigned to the purple tire of the car. And we redo that for the next hierarchy level, and so on, until we have a good match. So one thing that is also a key to success is that we always do the matching in the local coordinate system. So let's assume on a higher level, these 2 arms of these 2 robots have already matched. What we do then, we kind of look into the local coordinate system. So maybe these things are back projected into their local coordinate system. Then we look at the center of these parts. And then we just say, okay, which parts are closest to which? So the one down this one is closest to this center, and the upper one is closest to this center, and then we get a mapping. And you see this only takes positional information into account, but it's very powerful if you have very different shapes. So if you would say, I want to do shape matching between this and this is so different and it's so differently segmented, you would never succeed, right? So next is shape interpolation. There we have this slider interface, and the position of the slider tells us how many parts from the target object should be replaced in the source object. Well, we know now which parts to exchange, but obviously when we instantiate them, they appear at a totally different position. And so we use the contact analysis, the structure of the object, to build up a mass spring system, which always pulls parts to their correct position, because we know which parts should be connected. And here you see the mass spring system kind of in action. Okay, let's come to some results. So here the user selects the target shape and moves the slider. And as you see, there are many shapes that might be interesting that you maybe as a human wouldn't have figured out. Maybe you would have never assigned such big knees to this slim guy. So it's also nice to maybe generate some new ideas for artists. And not all shapes are look perfect, but some, you would maybe think, okay, this might be a suitable model. So we can also blend between different categories of shapes. So here you see a blend between a plane and a narrow plane. And though it's not perfect, some intermediate shapes are maybe quite interesting. You now see blend between two boats, and see they're completely different scale also. This has many levels, and this fisher boat or yacht has only one level. But because we do a resegmentation, this is no problem. It fits approximately, so we get a nice morphing result. You see the morph between two container boats. They have very similar structures, so the morph is quite good. More boats. You see a morph between an aeroplane with 4 jet engines and 2 jet engines. And also the wing structure is a bit different, so here you see it changing. And maybe once again, so there's no manual annotation. So this is purely from the data that is on the internet repository. We have some metal machinery. Okay. So, yes, so the discussion, obviously not all intermediate shapes are correct. This is natural for an automatic method, right? And another point is that morphing is more challenging than only exchanging some parts. So there are methods. So you could now look at all the methods, all the models that come out, have some criteria and say, oh, this one looks good, and only present the good one to the user. But if you have a slider interface where for each slider position you have to generate something, obviously it's much harder because there are also some which maybe even a human could not figure out how to assemble these parts, right? Yes?
Do these have interiors?
Do these what?
Do these models have interiors?
Yes. Yes.
So like chairs and...
Yes, yes, yes. It's as it comes from DOSH, so they are very detailed models. So the parts that you see are only a fraction of the parts that these models have.
So how does the interior look when you do this blending?
I don't know. I don't know. one problem that we have is that this typically works better on tree-like structures, because obviously when you replace a child, then you know the rest of the things knows exactly how to configure itself with the mass spring system. If we have interiors and they are very connected, then you have many constraints you have to fulfill, and obviously there are conflicting constraints which you cannot fulfill necessarily. And maybe then you need to a model which also allows to deform parts or these kind of things. This is a key simplification here. We avoid varying the geometry of individual parts. So maybe you have a door from one car which you want to fit to the door, to the space of the other car, but it does not fit. So it looks, you have an artifact there. Yes, so maybe semantic information in functional analysis would be useful. So we saw that whatever a boat was equipped with some jet engines, but because we don't have any semantic information currently, it's purely on positional information, we get semantically wrong recombinations. But what is maybe the key take-home message here is that positional information, if applied in this hierarchical fashion, is very, very powerful and a good tool to match shapes. So summary, I have presented a system to synthesize new 3D models from a database of many part shapes. One can blend objects that are highly dissimilar. It can help artists brainstorm ideas. It's well suited for non-expert users because it only has one single slider. And yeah, it also might be useful to generate a large amount of synthetic data shapes to maybe train computer vision algorithms. That's it.
So thank you very much. We have time for questions, and we have questions. So please.
All right. Physics. So it was not on your list, right? So you could simulate, like, if there is, like, I mean, you could also test probably if it's
yes,
light or
yes.
the material.
So there's this paper by Nidal Mitra or his group, How Things Work. You know this. So he really analyzes the joints, how they can interact with each other. But then you also need to assume that the modeler who designs this thing has really built it such that it would work, right? So, yes.
Dieter? Just.
Do you have any experience with using that on, let's say, noisier or incomplete models that you might build, let's say, from Kinect Fusion or something like that?
No.
Would you imagine that it might work? Or?
I mean, a key challenge is the segmentation. If you would provide the segmentation, I would assume it would work. I mean, noise is not a problem here. It's a very, very simple algorithm, as you might have noticed. It's just overlaying positional information, so there's not much that can go wrong. So I don't see noise as a problem.
Sven and then Reinhard.
There's much more information that you actually have than is available through the slider, right? So people could decide to first change the arms, then the legs, etc., etc.
Yes.
So how would you, maybe you elaborate a little bit on the possibilities of advanced user interfaces?
Yes, actually, when we first submitted this paper, we had all these user interfaces in there, and then they bashed the paper because we didn't evaluate them all, and so we took them all out. Yes, so we had a user interface you can pick apart, and then it suggests other possibilities and so on. But usually the thing that comes out of this is much better, of higher quality than what you see here. As I said, the blending is actually the harder bit. And if you can succeed here, you can also succeed in the other tasks. We also had a user interface where you can only navigate by semantic attributes. So you could say, I want to make the ship older, and we then would take parts from older ships or these kind of things. Right? So.
I wonder a little bit about the orientation of the individual parts, because they depend on this PCA we do at the very beginning, and this depends on not on the main axis of the object, but this depends on the distribution of points.
Yes.
Does this reflect in the reconstruction somehow? In your examples, not, okay? But maybe in reality, not. Yeah.
I mean, how do we use this information? We only use this to define a local coordinate system. So if this local coordinate system is maybe flipped or something, then we need to have it flipped on the other side as well. But this is no problem because we redo the segmentation on the other side. If we would do it independently, then if you had a flipped coordinate system, it would be killer, right? So you would match the underarm to the upper arm.
Does it need to be the rotated one?
Pardon?
If it rotates a little bit and you get certain sections then at the end, because your arms were always correct in your example.
No, I mean, let's assume, so you match two human characters. So first one has the arm here and the other has the arm here. So first you say only left and right. And left and right, those on the arm level, they match. And then we have a local coordinate system for this guy, a local coordinate system for this guy. And only in this local coordinate system you have to have then left, and right. And so is this what you meant? So it's
okay, if you rotate an arm, it doesn't matter because this makes sense. But in many parts you compose here, it does. It's how you organize it.
Yes, obviously. Also, we assume that they are all upright, facing north, these kind of things. Facing frontal facing. This is what we assume is done by the modeler in the database, or if not, we flipped it. And this kind of gives you the information that the head is not, on the other side. Exactly. Yes.
One thing I find fascinating is this huge discrepancy between what people of different levels of expertise would think about the results. And there's some things, I look at a robot and say, what's a really cool robot? A person who's designing robots, I look at it and say, it will fall over because it's obviously going to be top height because that piece has to weigh a whole lot more than you might think that it actually would. Or you have two pieces that when put together near each other might make for hydrodynamic properties that would essentially just not work. And even if you're an expert, you might not even know that. But of course, you could, in theory, be doing the analysis to figure out whether that was the case or not. So I think it's just really interesting how big a range you can get of what makes sense and what doesn't make sense.
Yeah, so you could, in theory, put this all on top, right? You could have this, build many models, and then have some objective function that tells you this is physically possible, this is maybe mechanically possible, this is maybe semantically possible.
So many more things than you need. It might be nice to have some of those models working from the bottom up, building those things out before they
Yes.
Have you tried transferring any motion between the models?
Again, please.
You try transferring any motion between the models. So if the bicycle wheel spins, you should get
It's another paper.
Any more questions? Yeah.
Dr. Acid, do you worry about things like contact, like that bicycle wheel really can't spin if it's bumping up against something else? Do you take that into account?
We enforce that they appear at the same position again, right? But we don't enforce here, but we could. It's that if they would intersect, that we ensure that they don't intersect. But it's a mass spring system, so these kind of constraints you could easily put in. We were just too lazy, kind of.
In the spirit of workshop discussion, the comment you made about the user studies seems like a really example of something really, really bad in the reviewing process that we should all watch out for. Like, if my impression of this is that you shouldn't need a user study at all for these, because the results speak for themselves. And it's really bad if your paper was made a lot worse because people would ask for quantitative evaluation. In this case, user study is just icing on the cake. So I don't have a question, but I just simply a comment. This is a comment about the whole reviewing process that we should be concerned about.
Yes. I think we had a user study, obviously. Yes. But it's more like then task performance, these kind of things. Yes. Did we have a user study?
All right, I'll second Aaron's remark and point out that on occasion you need a user study to persuade the referees for August conferences that the judgments that they think they can make, they cannot in fact make.
Okay, I think this is a good point to move on to the next paper. Thank you very much.